So in this video, we are going to talk about the concept of vapor pressure. Now, vapor pressure can be a little complicated, but we are going to try to simplify it as much as we can and make it as easy as possible. So what is vapor pressure? First thing, well, it is the force that a molecule has when trying to leave the liquid phase. Okay, and by leave, we really mean boil. So it's pretty much a force that will drive boiling or not. And now there are two forces we have to worry about, and I have them both here in my example. The vapor pressure is, again, so in the bottom of this diagram, I have a liquid, so think of this like a glass of water, and then there's a sealed top, and then the air, I guess the top actually doesn't need to be sealed, but so you have your air, and you have your liquid, and what we are focusing on is where the two meet. The surface of the water would be essentially what this is supposed to be showing. So when we think of water molecules, think of them as, they're moving around just like gas particles would move around, except not as fast. All right. And so they're moving around and they're going in every direction, but on the surface, some of them will go into the air. They'll basically jump into the air. And so when the vapor pressure is strong enough, they can actually jump into the air and push their way through the air and stay there. We call that boiling. That's essentially what causes boiling. I'll go into it in a little bit more detail in a second, but that's essentially what vapor pressure is, and what causes it is the movement of the molecules at the surface. So now, in your kitchen, if you wanted to boil water, what do? You take a pot, you fill it with water, you put it on the stove, you heat it up. And so what you're really doing is you're increasing the speed of the molecules, because remember, temperature is average kinetic energy, which is molecular speed. By making the molecules faster, you are then giving them more speed or more energy with which to jump into the air, and then they will be more likely. Eventually, you hit a point where they have enough speed and energy to jump into the air and stay there. Okay? Think of it like a fish jumping out of water. So if a fish jumps out of water, if it's not moving very fast, it jumps out of the water, and then gravity pulls it back down. And so what we're doing is we are speeding up the speed of these fish until they are moving so fast that they jump into the water, fly into the air, go into outer space, and never come back down. Obviously, it doesn't happen in real life, but that's the analogy I chose. Okay, so basically by heating them up, we make the molecules faster, and if you make them move fast enough, they can essentially push past the air and get into the air and stay there. We call that boiling. That's what we would see when we see the bubbles forming in liquid when we boil water. You all know, you've all seen that before. Okay, that is a direct relationship. If you increase the temperature, you increase the vapor pressure. You decrease the temperature, you decrease the vapor pressure. Now, the atmospheric pressure, the reason why liquids don't boil when they're under their boiling point is because the atmospheric pressure is strong enough to take the water molecules that are jumping into the air and just push them back down. That's why water doesn't boil all the time. A very specific condition has to be met. So just to review, if the atmospheric pressure is stronger than the vapor pressure, then the atmosphere will just push the liquid molecules that try to leave back down and nothing happens. That's every liquid you've ever looked at ever, except the ones that are boiling. Now, the way we make liquids boil is by increasing the temperature until the vapor pressure becomes greater than or equal to, don't forget the equal to, that's important, the atmospheric pressure. And once that happens, the water molecules can push past the gas and get into the air and stay there. That's when liquids boil. Now, there is another way to make liquids boil, because remember, we just need to make these conditions correct. So by increasing the temperature, we increase the vapor pressure. Another way of making a liquid boil is to actually remove the atmospheric pressure and reduce it until liquids boil. And you will see in a lab at some point, we will make water boil pretty much in the palm of your hand. And the way that we are going to do it is, instead of increasing the temperature / vapor pressure, we are going to reduce the atmosphere and remove the atmosphere from the equation, and that would boil as well. So we can do it both ways. But on Earth, in a kitchen, we're always just heating up water. That's how we do it all the time. But under special circumstances, you can do the reverse. Now, the types of questions you're going to get from this are going to be almost exclusively from Table H in your reference table. So Table H looks like this. Here's a couple things to be aware of. On the X is the temperature. It's 5 per box. That's the scale. On the Y, it's vapor pressure. It's 10 per box. That's the scale. Do not confuse that. I do it all the time in class. I will probably do it in front of you. It is very easy to confuse, and I'm the one teaching this, so be very careful. Also, this dotted line is our standard pressure. So this, if you remember STP, this is the standard pressure part of it, not the standard temperature. So The thing to be aware of is the dotted line does not represent 100. It's 101.3 or 1 ATM. So just be careful there because they tend to like to ask questions around those to see if you remember what the dotted line means. Now, what do these lines represent? Well, they represent the boiling points for these 4 compounds: propanone, ethanol, water, and ethanoic acid. If you don't know what all of them are, don't worry about it. By the end of the year, we'll know all of these very well, too well, as some of you may agree. Now, let's do some questions, and I'll show you how it works, and it's very simple. So, what is the boiling point of ethanoic acid at standard pressure? So the line represents the boiling points at any given temperature and pressure, and so here's what we do. We go to standard pressure, which is our dotted line. We follow it across to the ethanoic acid. We then drop a line. Once it hits the line, we go all the way down, and then we put a line here, try to estimate what this number is. So this would be 105, 110, 115. This is 120. So I'm going to guess that this is somewhere between 116 and 119 degrees C. So that would be any number within this range is fine. Now be aware, 115 is not acceptable because that would be this line, and 120 is not acceptable because it would be this line. So it's got to be somewhere in that range, and depending on the teacher, some teachers may even want 117 to 118 because 19 would be really close to this edge and 16 would be really close to that edge, so they may even ask you to restrict it a little bit more. I'll accept anything in that range. Number 2, what temperature will the boiling point of water be if the atmospheric pressure were 50 kPa? So you go to 50 kPa. You then draw a dotted line, or you could draw the line or just follow it over, all the way over to water. And then once you hit water, you go down and you estimate that temperature right there. So I'm going to call this line is 80, so we'll call it 81 to 83 or 4. Anything in that range is fine, and that's how you do it. Okay, so this chart works in both directions, as long as you're either going to be going take a temperature and go up and then over to a pressure, or you're going to get a pressure and you're going to go over and down to a temperature, and that would tell you the temperature that it would boil at, or if it was at that temperature, the pressure that you would need to make it boil as well. We'll do a few more. At what pressure will ethanol boil if the temperature were 50 C? So you go to 50 C, you go to ethanol, which is all the way up here, and then if you look, this one's a good one because it's slightly under the line. So we draw a dotted line over and it's like right there. Okay, maybe, but if you look carefully, it is definitely under that line at 50 C. So when I estimate my answer, 10, 20, 30, I'm going to call it like 27 to 29 kPa, somewhere in that range. I'm not, maybe even 26, but I'm definitely not going to call it 30 because 30 would be the line and it's clearly under the line. So that would be the pressure needed to make ethanol boil if the temperature were at 50 C. And then what temperature will propanone boil at 1 ATM? Again, they like this question because the ATM part isn't written in. They only give you the kPa. They're then expecting you to know that 101.3 kPa is 1 ATM. I would write that in here and here in your reference table. So then you just go to the dotted line. You go to propanone, which is the very first one, and you see that it's a smidge over. So then when I draw my dotted line down, it's going to be like 56 to 50, maybe even 58 degrees C. I'd even take 59, but technically if you look, it's much closer. It's kind of in the middle, so I'd take something like that. So that's how you use this chart. That is everything we need to know about vapor pressure and its relationship to temperature and when things do and do not boil.